I am going to turn the podium over to our first speaker, which is Phillipe van Cappellen from the University of Waterloo, who will talk to us about damming of rivers as drivers of global environmental change.
Good morning again. There it is. So Howard and I actually were meant to meet because we both came to Canada as part of the first batch of Canada Excellence Research Chairs. And of course, we share a passion for water and water issues. But maybe more pertinent to today's talk here is that a couple years ago, I and my then graduate student or PhD student, Taylor Mavara, actually came to Saskatchewan. And we had the opportunity to actually go and have a trip on Lake Diefenbaker, which is one of the largest reservoir lakes here in Canada. And it was Howard who organized this trip. It made it possible. So I think it's only fair that today I'm reporting on where this research actually led. So first of all, about dams. There's very, very many dams. Their estimates are, of course, very variable, but there's probably over 16 million dams worldwide. And if you take, of these 16 million dams, probably 70,000, more than 70,000, probably qualify as large dams. And by large dams, we mean dams that are 15 meters in high or higher. And if you take all the reservoirs associated with these large dams, then they cover a surface area of over 400,000 square kilometers. And just to put that in perspective, if you take the Laurentian Great Lakes, all the 5 Great Lakes together, their surface area, their combined surface area is 244 square kilometers. But the big difference between lakes and reservoirs is that we keep adding more and more reservoirs as time goes by. And so if you take, for instance, the global river catchment area that drains into large dams, in 1970 it was about 18%. By 2000 it was 27%, and the projections are that by 2030 it will be on the order of 36%. So large, huge area, lots of dams, and also a lot of the water that is flowing on the continents actually ends up having to pass through dams. So here's a map, didn't come out too well, showing the distribution of a fraction of the large dams. And in red, it's the dams that were in existence in operation in the year 2000, at the turn of the century. So you can see that there's some hotspots, in particular here the continental United States, but also Western Europe, China, India, etc. And in blue is actually dams that are currently under construction or at least planned to be finished by 2030. And this is from a compilation by Christian Zarfel. And you can see here the title of her paper. It's a global boom in hydropower dam construction. Because most of the dams are being constructed nowadays are actually being built to generate electricity, mostly for actually emerging economies in, say, South America, but also Southeast Asia. So that gives you an idea of the global distribution and therefore the global impact of dam construction. And in fact, to put that in perspective, it's estimated by 2030, 90% of all rivers will be fragmented by one or more dams. So I think it's no exaggeration to actually position that the damming of rivers is probably the largest single anthropogenic modification of the freshwater cycle. So the question that we were trying to address is, well, how is all this changing the flow of nutrients along rivers? And of course, this is part of a broader interest of us, or me, in the fact that as humans, we're putting more and more nutrient elements such as nitrogen and phosphorus into the environment with a lot of negative impacts on the quality or the aquatic or water quality in aquatic ecosystems, and also leading, for instance, to these algal blooms. So we've worked on carbon, we've worked on phosphorus, we've worked on nitrogen and silicon. For the moment, we're working on nitrous oxide. So I'll take just one example, and that's phosphorus. So phosphorus is an element that, to a large part, tends to stick to particles or be associated with particulate matter. And in a reservoir, these particles sediment, and so some of the phosphorus that enters the reservoir actually stays in the reservoir. And so in general, when you measure phosphorus coming out of a reservoir, there's less coming out than going in, and that's what we refer to by this phosphorus retention. So we said, okay, well, let's try to make an estimate of the global phosphorus retention by dams. And so when we started, or when my PhD student started, Taylor, the problem she encountered was she could only find 155 reservoirs with complete phosphorus budgets. So these are reservoirs for which we actually know how much comes in, how much goes out, so we can actually calculate directly from the data what the phosphorus retention is. In addition, most of these 155 reservoirs are either in North America or in Western Europe. So there's also a geographical bias. So bottom line is the available data is certainly not statistically representative of all reservoirs or phosphorus retention in all reservoirs across the world. So how do we go around that? Well, start from the realization that actually the processes that will control, say, phosphorus retention in a reservoir are the same processes that actually control the cycling of phosphorus in natural lakes. And phosphorus cycling in natural lakes has received a lot of attention. So we know a lot about those processes, so we can start building models that incorporate the processes that we think are the most relevant in terms of calculating phosphorus retention in reservoirs. Now, if you do that, and we use fairly simple models, even these simple models then basically end up with a whole bunch of model parameters. So what we do is we take all the information that's at hand, so information could be field data, could be experimental data, could be theoretical information, to then define probability distribution functions for all of these parameters, and then we can do fun and games. We can do Monte Carlo simulations, where we randomly choose the values of these parameters, run the model, and do this over and over and over again. So essentially what you create is a virtual reservoir database. So those are not real reservoirs, but the assumption is that the dynamic behavior of the reservoirs in this virtual database are similar, or at least sufficiently similar to that of real reservoirs. And so then we can start establishing global relationships. And by that what I mean is that these are relationships, or that we're trying to do is to relate the properties of the reservoirs that we want to know, for instance, the phosphorus retention efficiency, but for which we have very little direct information, to then metrics of reservoirs for which the data availability is much larger, such as the location of the reservoir, so the altitude, the latitude, the dimension of the reservoir, so the physical characteristics of the reservoirs, and in particular, the water residence time in the reservoir. And so once we have this global relationship, we can let them loose on the databases of actual real reservoirs. So that's the approach that we're using. We call it a knowledge-based scaling up because, of course, the alternative would be an ignorance-based scaling up, right? Okay, you got that. Now, we still need to know how much nutrients, say phosphorus or nitrogen, actually enters into reservoirs. For that, we use the so-called global news model, which stands for nutrient export from watersheds. And those are actually a series of empirical relationships that take characteristics of the watershed, including population density, things like the GDP, climate, hydrology, water management, land use, nutrient management, and then relate that to the nutrient yields. And so nutrient yield is essentially how much, the mass of a nutrient, a given nutrient, that is loaded to a river per unit of surface area of the watershed per unit of time. And the nice thing about global news is that for each one of the elements that we were interested in, carbon, nitrogen, phosphorus, and silicon, it actually gives individual relationship for different species of that element. So DIC stands for dissolved inorganic carbon, dissolved organic carbon, particulate organic carbon, and so on. All right. So so once you have your reservoir somewhere, what you need to know is the surface area of the watershed upstream of the reservoir. You multiply that by the yield, and you should be able to calculate or at least estimate roughly how much nutrient or particular species of a nutrient comes in. And so for the catchment area, we rely on a very high resolution geographical database that for all the reservoir, or all the reservoirs, all the dams in that database actually gives you the catchment area, and for the yield we use this global news model. So then we can do this analysis for any watershed, small, large, bigger, and so we can extend our analysis to entire continents and entire, or even the global scale. So that's what we're doing here. The nice thing also about the global news for these yields here is that global news also makes estimates for what these yields used to be in the past, so at certain time points in the past. And it also does predictions for the future based on these famous Millennium ecosystem assessment scenarios. If you want to have more information, we can talk about that later. So what do the results actually look like, or what kind of results can we get out of this type of analysis? So I'm showing here, for instance, this should read total phosphorus. So, so we're looking at the total phosphorus export by rivers to the coastal zone. As you can see, it's broken down according to continents here. You can break it down according to watershed if you want, or river basin. And everything is relative to the 1970s values. So if, for instance, if you look at the blue bars here, Those are estimations for the year 2000. So if, for instance, what you see here for Africa, we have a higher export of total phosphorus in 2000 relative to 1970. One of the continents where actually things are going down is Europe, and that's because of all the environmental regulations and measures to reduce the emissions of phosphorus. But what really jumps out here is, of course, Asia, where you see this large increase in the total phosphorus export to the coastal zone in 2000 relative to 1970, and that's, of course, due to population growth, the use of more fertilizer, more wastewater, etc. The other bars correspond to projections for the year 2030. AM stands for adaptive mosaic, GO for global orchestration. Those are two of the 4 Millennium Ecosystem Assessment scenarios. And if you look at the green, the light green, and the dark green bars here, it's the scenario for no new dams. By that I mean that essentially we run a forward projection, but we assume that no dams are being built between 2000 and 2030. This is, of course, wrong. I mean, we know dams are being built, but that's a nice thing about a model. You can basically shut out these dams. And what you see, for instance, again, if we focus on Asia, you see, again, a very large increase in the total phosphorus export from Asia. And then we repeat those scenarios, but now we actually allow the new dams, the dams that are now being constructed and or will be finished by 2030, we allow them to exist and to come into existence, and you can see that then the export actually drops down to practically the same level as in the year 2000. So the two things I want you to get away from this graph is, first of all, different continents can have very different trajectories, right? And that's expected. In addition, what you see is that the effect of dams is actually fairly substantial. I mean, here we go from essentially a nearly doubling of the export of phosphorus in 2030 relative to 2000, back to a level that is very close to 2000. We also see changes, for instance, here, if you look at Africa, without or with dams, we see essentially that we have either higher export of phosphorus or lower export of phosphorus relative to 1970. So we see this for phosphorus, we see this for nitrogen, for silicon, for carbon. Just as another example, if we look at organic carbon export to the coastal zone, for instance, if we focus on this here, you can see that according to our estimates in the year 2000, 13% of the export of organic carbon, that is the organic carbon carried by rivers to the coastal zone, actually was eliminated either by burial or by mineralization by the presence of these dams. And in 2030, this could be up to about 1/5. Now, this has huge consequences for the trophic state of the coastal zone, because this is organic carbon that would have gone to the coastal zone, would have been respired there, and it now is being respired in the reservoirs. And so this is one of the reasons, not the only reason, but it's one of the reasons why we're seeing that worldwide coastal areas are actually turning from being net CO2 producers, net CO2 emitters to the atmospheres, to becoming sinks for anthropogenic CO2. All right, so we can do this element by element, and of course we can then also look at the relative fluxes of nutrients delivered or carried by rivers. In particular, we've been looking at the relative delivery of nitrogen and phosphorus by rivers to the coastal zone. And as you probably know, marine phytoplankton, when it grows, when it forms new biomass, actually tends to fix nitrogen and phosphorus in a fairly constant ratio. That's known as, by oceanographers, as the Redfield ratio. It's named after a person who was actually called Redfield. And so we have this magical 16:1, which means that for 16 nitrogen, you fix 1 phosphorus. Which means that if a river is carrying to the ocean water that has a nitrogen to phosphorus ratio smaller than 16, it will tend to shift that coastal environment to nitrogen limitation. If the nitrogen to phosphorus ratio is higher than 16, you would shift the system towards phosphorus limitation. And that's very important from the viewpoint of nutrient management in the coastal zone. The assumption generally is that most marine environments, including coastal marine environments, are nitrogen limited. What I'll show you is that, in fact, with damming, we're tending to push the systems or the coastal zone more and more to phosphorus limitation. Okay, that's shown here, for instance. It's not a trivial graph or a map to understand, but essentially what it shows is the effect of damming on the nitrogen to phosphorus ratios delivered by rivers discharging into the coastal zone. So we have a coastal segmentation model here, and we're looking at, again, simulations with and without dams. And when the colors are green, it means that essentially the presence of dams in the watersheds discharging into the coastal zone, that the damming is actually pushing the system more towards nitrogen limitation. And there's a couple areas here, for instance, that you see are green. But for the most part, what you see is the color orange or orangey or brownish towards red. Those are essentially when the presence of dams is actually pushing the system more to phosphorus limitation. And this is a consequence of the fact that in general, dams or reservoirs are more efficient at retaining phosphorus than eliminating nitrogen. But this is for the year 2000. So now let's fast forward to the year 2050, and you see far more red color appearing on this map. Again, indicating that the continued construction of dams, plus also some changes in the nitrogen to phosphorus ratio of loadings to rivers, is actually going to push more and more the coastal zone towards phosphorus limitation. So the conclusion of that is really that river damming causes a worldwide shift towards coastal phosphorus limitation. And again, this should be important for coastal nutrient management, because essentially, if you want to reduce, for instance, eutrophication in the coastal zone, you have to work on the limiting nutrient. If you decrease the non-limiting nutrient, it's not going to have a lot of impact. So just finish up with a couple messages here. River damming represents one of the major anthropogenic modifications of the continental cycles of water, but also carbon and nutrient elements. Damming creates new biogeochemical reactors along the river continuum, so we're constantly adding new human-made lakes along the river continuum, and the processes in these reservoirs tend to decouple riverine nutrient fluxes. In particular, the elimination of phosphorus tends to be more efficient than nitrogen, and in itself, this would promote phosphorus limitation in the receiving water bodies. So that's true not only for the coastal zone, the coastal marine zone, but of course also for lakes. And so we propose that damming may be co-responsible for the progressive increase in phosphorus limitation of coastal primary production. Anthropogenic nutrient loading plus damming is also causing river systems to become more autotrophic with time. I didn't really go into that, but essentially most pristine rivers in their natural state tend to be heterotrophic. Organic matter is loaded from the landscape into the river where it gets respired, and CO2 is emitted to the atmosphere. But because of the existence or the creation of all these reservoirs, in fact, we are slowly starting to reverse this. And in fact, over the years, dam reservoirs are becoming more and more important sinks for anthropogenic CO2. And then finally, the largest changes in river nutrient cycling by damming will take place in Asia and South America, simply because that's where most of the new dams are being built. And I think that's it. Yeah, thank you.
Questions from the audience?
Thanks for the talk. Interesting that you ascribe so much of the impact of NDP changes to the reservoirs. But there's another competing hypothesis that regulation of phosphorus and not nitrogen has resulted in excess N export to the oceans.
Yeah.
So how do you take that into account?
Yes, so everything I said is really to say, okay, what happens with or without the dams? So it's the relative effect of the dams. Now, what we see is for certain reservoirs, there's actually more nitrogen coming out than coming in, dissolved nitrogen, because reservoirs are also hotspots for nitrogen fixation. So we actually, and it's a significant, well, this is the third author, Zara. She has actually done these calculations, and so it's a significant amount of nitrogen fixation that takes place in reservoirs. So we're actually increasing nitrogen fixation on the continents by essentially creating those reservoirs.
Okay, thanks. Yep. I have a follow-up if no one's going to. Oh, sorry. No, I've lost my train of thought. It's okay.
Very interesting talk. It was great because I also work on dams and from a different perspective. Mm-hmm. But I think, what I understood, perhaps please correct me if I'm wrong, but what I understood is that all these projections happen if the dam management stay as it is today. So how we can represent that dam management effect on nutrient balance, and also the point is that with with the very small sample that you have, and this kind of like a very nice way that you could upscale that and extrapolate it to other dams, would it be how it can actually that methodology reflect the dam management?
Yeah. So first of all, the type of models that we're developing don't have the temporal resolution to really take into account, say, the seasonal management or the temporal management of the dams. So these are very rough estimations. Now, and what this really means is that these are models that you should never apply to a particular individual dam, because it's going to give you the wrong answer. But it's essentially when you start upscaling, when you start adding more and more dams or reservoirs into your analysis, then essentially the uncertainty actually decreases and the collective behavior is going more and more towards the mean scale. So to answer your question, we really need a different type of model that has a higher temporal resolution, but also a much better spatial resolution. But it's something that we're really thinking about, because essentially by modulating the operation of the dam, you can actually for instance, release the nutrients at the most favorable moment, for instance, when the temperature is too cold for the algae to respond, etc. So there's definitely a potential there to use dam operation to minimize the downstream impacts. Now, of course, sometimes it's a give and take. For instance, I know in the region where I am, the dam operators mostly worry about what the cottage owners around the reservoir think. So if they think about management, they want to minimize, for instance, eutrophication in the reservoir. But sometimes you'll have to increase eutrophication in the dam to have less eutrophication downstream of the dam. I think we have time for one more question over here.
Thank you for the very interesting talk. My question is, do you have any insights for the eutrophication in the dams? I mean, certainly dams are very important for trap nutrients and especially the sediments. But over long term, it may become, as a sink over long term, it can also create eutrophication problem.
Yes. No, you're totally right. So the age of the dam or the age of the reservoir is extremely important. So we try to take that into account in a very simplistic way. But there are examples where there's an old dam that drains into the river draining into the Chesapeake Bay, which used to be a net sink for phosphorus and is now becoming actually a source of phosphorus because there's been so much sediment accumulation that now it's starting to bleed out. So the time is, of course, very important. And so the question will be, when all these dams are starting to age, can we really predict how they will also change? So the advantage that we have is that we have, of course, dams of a wide variety of ages. So by doing a comparative analysis, we should be able to tease out these aging effects. But you're right. I mean,
I'm more like ag people. So so my interest is always the land management and etc. So have you tested how the different land management scenarios can impact the efficiency of dams in trap sediments and nutrients?
Yes, so land management is of course important because of the sediment supply, and that determines the sedimentation, so that determines the retention of phosphorus, etc. We haven't tested it explicitly except in those Millennium ecosystem assessment scenarios where actually land management is one of the drivers of the loading of nutrients and sediment to the rivers. We haven't done it explicitly, but implicitly it's in some of these. So that's why, for instance, you see big differences between this global orchestration versus the adaptive mosaic scenario. But it's something that should be done in much more detail.
Okay. Thank you
very much. We have to move on.